Hi everyone, good afternoon. I'm Karthik from marketing team of EDS Technologies. We would like to thank you all for joining this interactive webinar on additive manufacturing, driving the future of automotive industries. Without taking much of your time, let me begin this session with the introduction of our speakers. Today we have with us Mr. Lakshmi Narayan. He is a national manager for additive manufacturing and ergonomics from EDS Technologies Private Limited. And along with that, we have Mr. Arun Kashyap. He is a technical manager additive manufacturing from EDS Technologies Private Limited. And we have a special guest speaker for today's session, Mr. Joe Ajay. He is a business development manager as well as a technical consultant for additive manufacturing from EOS. As displayed on your screen, this is the agenda for today's session. The session will begin with a small introduction about EDS Technologies Private Limited. Thereafter, our industry experts will take you through a world of additive manufacturing, its applications in automotive industries, and along with the real-time examples and case studies. Now, I would like to request Mr. Lakshmi Narayan to begin this session with the introduction to EDS Technologies. Over to you, sir, and happy learning to you all. Thank you.
Thanks, Karthik. So, very good afternoon and good evening, and warm welcome to all my respected customers. So, once again, thanks for taking your time actually and interest and joining in today's webinar. We will ensure that you will be having best takeaways by end of the session on additive manufacturing technology for automotive industries, especially. We, as an EDS Technologies Private Limited, started our operations in 1994 in product lifecycle management solutions. And also, we are the premium platinum partners to Dassault Systems from starting of our journey. We have more than 2,000 plus customers till date. And we have even 9 offices across India and headquartered in Bangalore with best organized structure carrying into all departments. So we are the first one who brought actually the 3D printing technology of FDM to India in 1990s, which is nothing but Z Corp machines. And we felt it was too early in the market, and we partnered with EOS in 2019, and our journey is going along with our customers very successfully till date. Coming to our business solutions, we have 3 verticals: technology solutions, learning solutions, and services. As I priorly informed, we are partnered with Dassault Systems, providing business experience platform with industry solution experiences for 3D design analysis, simulation, and intelligence software in such a collaborative and interactive environment. It is also available in on-premise and on-cloud as well. Basically, coming to this product portfolio, 3D experience, CATIA for design, and Simulia for realistic simulations like example Abacus, and Delmia for digital manufacturing, and Innovia for collaboration and integration of all the softwares with seamless data integration. And coming to Ramsys, it is like a humanetics from humanetics for it's a purely ergonomic solution to analyze the comfort analysis of a human for passenger vehicles, bus and truck, two-wheeler, tractors, aerospace, and so on. And another solution is QChecker, which helps in integration with CATIA and helps to quickly do the quality check for CAD and drafting, and it is from Technia. We have also solutions from mining from Dassault Systems and visual simulations from Mac. It is purely for defense sector where you can do pilot simulations and wargaming and so on. Coming to GIS solutions from ESRA, it is especially automotive. If you see EV companies, they can take an advantage of demand generation within the solution, like where exactly the population is more who are driving EV, which makes you quick decision on the charging station location on a prediction point of view. And along with that, there will be the best service center. Where will be the best service center to put? Showrooms. And you can do lots of market analysis and decide within no time. And coming to our today's topic, 3D printing, we are partnered to EOS, Electro-Optical Systems, based out of Germany, and Munich is the headquarter. We have industrial grade solutions from polymer and metal technologies through 3D printing, and 80% of the global automotive OEMs are with EOS. and 70% of the metal contribution and 50% of the polymer contribution in India are also with EOS along with EDS Technologies Private Limited. And coming to the next, we have e-learning solutions as well developed by us, and it's our own baby product. We have dedicated consultancy team for implementation of the entire out-of-the-box process like design, change management, integration with ERP, project management, and so on. Hope you understood about us, and now we will make to continue our journey dedicated to additive manufacturing going forward the session. Thank you. Over to you, Arun.
Well, thanks, Lakshmi. Hi, everyone. Good afternoon and good evening. My name is Arun Kashyap. I have 7 years of experience in design and development of prototype manufacturing using rapid prototyping methods, RPTs. I'm a full-time AM technology promoter and a consultant working as the national manager to handle additive manufacturing in EDS technologies. Welcome you once again to our webinar, and thanks for making it possible to join us out of your busy schedule. I'll take you through the mid-section of this webinar, and I really hope that you'll enjoy the session. To begin the webinar, we'll begin with the prototyping concept. What's prototyping? So I think most of us know the prototyping has been being used for years to replicate the ideas and concepts whenever we have an idea during the product development cycle. Now there is a term uh, popular in the industry, which is a rapid prototyping. So what's basically a rapid prototyping is it's a method to manufacture the physical part directly from its CAD using various techniques, and it can be used at any stage of the product development cycle, iterations, and repeatedly it is possible with the feedback during product development cycle. You can change the designs, you can do the multiple iterations. And rapid prototyping has seen its application whether you want to make a visual part just to look aesthetically, or whether it is your concept model or it's a functional prototype. You can use the prototyping even before production. You can use prototype for your toolings also, and production of the molds for the prototyping and pilot batches. Typically, rapid prototyping techniques are available in the form of additive manufacturing, vacuum castings, investment casting, CNC machining, carving. Um, People use soft tooling also. Laser cutting is being used, sheet metal fabrication is used, and there are many other technologies and techniques used in the rapid prototyping method. So here is one example we have shown. Basically, rapid prototypes are categorized widely from low fidelity to high fidelity based on the requirement. You may require any kind of prototype development. So in this webinar, we'll mainly be focusing on the additive manufacturing. What's additive manufacturing? So additive manufacturing, it's very simple to understand with the concept that you see the stages are there. You have a CAD model, and you slice the CAD information into hundreds and thousands of the layer, and those layers are cured by a particular method, and that's how you get your final model through the 3D printing. Based on the materials available in the market, the additive manufacturing have been classified into many other types. The types are like based on the powder, selective laser sintering, SLS is available, then selective laser melting is available, electron beam melting is available, and then there is a technology, DMLS, direct metal laser solidification, and powder-based binder jetting and MJFs are also available. Then when we call a solid material, typically the solid material based technology is called as fused deposition modeling, which I think most of us are aware, the FDM technology and triple F technology, which is the fusion filament fabrication. And the third type is when the raw material is in the form of resin, we have a stereolithography, which is a SLA. And nowadays there is a trending technology, which is digital light processing, DLP. And finally, ink-based technology is available, which is multi-jet modeling. Moving forward, looking at the landscape, whatever technologies nowadays available for the rapid prototyping, uh, the most promising in the form of part quality, the powder bed fusion technology is something which is more reliable and give you the prototypes uh, with a very high quality. So it's very evident from the study given by Ford that the powder bed fusion technology is very trending out of all options available for rapid prototyping through additive manufacturing. Yeah. If we talk about performance-based AM technologies, so here we have focused mainly on metal-based additive manufacturing technologies, whether it is a laser-based powder bed fusion, or it's a direct energy deposition, or material jetting, or powder bed fusion, electron beam-based powder bed fusion, and wire-based DED, or material extrusion. There are several technologies available in the metal also. So we have seen that laser powder bed fusion has been having the highest potential to reduce the cost, and it's very promising in the form of when it comes to part performance and part cost. It's been showing remarkable results when it comes to the end product of the prototype, or any functional component. In a recent technological survey, when we asked to 87 approx 87 AM service providers from different countries, we saw that their end users, it's very much evident from the graph that their end user has been asking for the powder based and especially the laser based powder bed fusion technology, which is SLS and DMLS. 61% of the responses were towards in the favor of SLS technology and the DMLS technology. So now we have seen the different kinds of technologies available. Few of those are emerging technologies. Few are very old technologies. Um, with this, we'll begin with our laser-based powder bed fusion solutions. So, what are exactly laser-based powder bed fusion? Raw material is basically available in the powder form, and in case of polymer, what is the differentiation here basically is the systems are different. Just to understand, polymer systems will handle the polymer materials, and metal system handles the metal materials, and they are different to each other with the fact that in polymer we heat up the powder, we sinter the areas, the cross section of the material with the CO2 laser, and we we can reuse the powder in this SLS technology, and there is no support structure required in the polymer scenario. When it comes to metal, it's completely a cold process with the fact that the powder doesn't get heated. In case of metal, it uses a, fiber laser, and it's slightly a high laser power, and all powders are reusable in this case as well, and you get some amount of support structure. So later on we'll discuss in the webinar how those support structures further can be eliminated. So we'll begin with our first solution, which is SLS technology. So what's SLS technology? SLS stands for selective laser sintering, as I earlier mentioned. It uses the laser directly to sinter the material, and the curing is very fast within the chamber. The printing happens within a closed chamber. SLS technology is available in polyamide, in elastomer, and styrene-based materials. The operational stages are quite simple. It's very easy to use the SLS technology, EOS-based SLS systems. It's just involve the stages like material preparation and filling and printing of the material. Then we unpack the printed materials, we depowder the components, and we do some sort of bead blasting, and then your parts are ready to be used directly as a functional prototype. The benefit of SLS technologies are you get a fully functional and reliable part without a tool. So it's a tool-free technology, and it doesn't involve any support structure. So it's very easy when it comes to post processing. You can directly use your component just by doing nominal finishing. It's available in high precision and more accuracy form also. So there is another laser which we use, and we call it a fine detail resolution, which is FDR, and it's pretty accurate to detail the feature of your component. The materials of SLS are high in mechanical properties. The laser process is fastest curing among all processes, because it just had to scan the area, and once all layers are finished up, your parts are ready. So it's quite fast. And the SLS parts are most economic when it comes to cost per part. So unit cost when compared to all other processes, the SLS technology gives a great and better unit cost. And it's fastest when it comes to pre and post processing. It's very easy to uh, get the machine ready for the printing, and do the post processing and get the parts ready for further using the parts using it. And the materials of the SLS are biocompatible and less hazardous when it comes to the operations. You don't need literally any cleaning agents later on when you print the parts. So it's very good to handle. It's very easy to handle the EOS SLS technology. Moving forward, what are the factors which better positions the SLS technology among other powder-based technology available in the market? So this SLS technology is available with the purely polyamide based material, and you get your part just like the injection molding does. In injection molding, typically you press the heated material in a cavity of the mold, and you get your part. Likewise, in 3D printing, in SLS 3D printing, you heat the cross-sectional area and you melt that particular area to form your 3D printed part directly. There is no filler, or there is no binding agent or detailing agent required in it. So further, it doesn't have any cost involved, and any challenges and timeline challenges involved in the process. It's just quick process that you just start your build, and next day you get your part. Um, though there are natural form of the polyamide available, there are other form of the materials also available. You can get a like injection molding, you can get a glass filled material also, and you can get a carbon fiber and aluminum filled material also. You can get a fire retardant materials, or fire retardant materials are FR classified and certified materials. With SLS, you get a faster curing, as I earlier also mentioned, that the laser is so fast that it scans the cross section in a very quick manner. Typically talking about our mid machine, which is completing its cycle just within just 1 day. So it's pretty faster. You get the whole bit build printed within 24 hours. And uh, the SLS parts are better in quality, and you can fill as many parts as possible within the build chamber to densify and to leverage the space inside the SLS printing chamber. So doing this, you can have a best-in-class productivity and least cost per part. It's available with exchangeable frames and all other accessories, which minimizes the change over time. So that's how the SLS technology is on top of any other technologies available in the market. Coming to SLS versus FDM comparison, so there are many. There is no first of all apple to apple comparison of the SLS technology and the FDM technology. However, sometimes in industry people have mindset and they correlate the 3D printing uh, directly with the FDM, because it's more seen in the market. So they feel 3D printing is only available in FDM, but FDM is a very initial technology, and it's very basic technology. With the FDM, you can print part for just for the realization, but you cannot use them as in good manner as you can do with the SLS parts. So when it comes to cost, the SLS parts you can print literally without no support structure, so there is no additional cost involved in the SLS process. While in the FDM, you have to invest some amount of the uh, dissolvable or non-dissolvable supports that will be again hectic when you go to post process them, and it involves many costs to increase the per part cost. And the materials that are available in SLS are all industrial grade certified materials, which are biocompatible and fire retardant compatible. They're leak proof. They've been tested for the leak proof, and there are many more certifications available with the SLS materials. While FDM materials are very basic, and it's just to realize the concept of the model or the CAD. When it comes to time involved of printing, SLS, the way it treats and it cures the material inside, it's very fast in many ways, and it's comparatively faster than any other technologies available in the segment. And FDM is at the slowest of the when it comes to the printing speed. When we discuss about the quality, the material properties are similar to injection molded or pretty close to injection molded in SLS, but in FDM, these are lower than injection molded most of the time. As I said, the quality is not been up to mark. All SLS materials, most of the SLS materials are already used in the flight applications. They are certified and approved for flying. So and SLS materials are available in black, white, and gray, but later on you can paint them. You can do the post processing as per your application. You can use them. FDM materials are available in many colors because of the fact that they can be used for fancy models and all. When it comes to choose the additive manufacturing or any polymer material in the application, you have to decide on certain criteria like service temperature or heat deflection temperature, or the kind of the polymer, whether it is chemical resistant or water absorbing polymer, or it's whether it's a commodity polymer or it's an engineering polymer or it's a high performance. So in SLS EOS SLS systems, we have various categories of thermoplastics and few amorphous materials along with us. We have polystyrene based material. We have a broad category of nylon based material, which is engineering plastic, offers you the service temperature more than 110 and 120 degrees at least, and even more with the glass filled and carbon filled materials. Then we have high performance polymer alloys with us, which I'll discuss later. So this is what is available now with the EOS systems. We have polyamide 12 material. So we have a natural form of polyamide in black and black pigmented and white. And we have fire retardant material, which can be used for all electronic and electrical applications, and wherever the fire retardant feature is required. And we have a glass filled material wherever a tough wherever the stiffness is required in the application. And we have exclusive polyamide material, which is a mixture of polyamide and aluminum. Then we have a polyamide 11 material also available with us, which is more elastic compared to polyamide 12. And all these polyamide materials are very much uh, uh, reliable, and they can offer you the properties in a very good way that none other technology can give. And then we have prime cast and polystyrene based material, which are used typically for the investment casting process and in packaging industry. We have elastomer, which is urethane based thermoplastic material used for your seat or cushionings or any kind of application which require the rubber like properties. And then we have a high performance polymers, which are PEC carbon filled and PEEK material HP3. These all materials are processable through EOS systems. So when we call polymer high quality materials, means we mean it with the fact that the properties which are tested on all material are up to mark. So let's see what the property says. We have prepared a comparison, the thorough comparison between the injection molded materials and the additively manufactured materials. So here with the red color ESP 2200 and ESP 3200 glass filled material are laser sintered material, and you can see the results. They are directly comparable with the injection molded, even PA6 material, and slightly better than PP material when it comes to mechanical properties, slightly poor in elongation. It's way more better than ABS material, injection molded ABS material, and it's better than even injection molded polyamide 12 material. So when we talk about a material, when we talk about supply chain, when we talk about the manufacturing, we have to consider what environmental impact we're leaving behind. So all these materials are designed and manufactured in such a way that they have a very less carbon footprint. So compared to natural form of Pa2200, our carbon reduced Pa2200, US Pa2200 carbon reduced has 45% less CO2 emission footprint, and Pa1101 has 54% less carbon emission footprint. And subsequently, Pa1101 is very negligible. It's just out of this carbon emission almost. So EOS SLS materials are all well certified for fire retardant applications, well certified for biocompatibility. And we have even tested the polyamide SLS printed components for the leak and air tightness, as well as the water resistance. So the material has shown a significant water resistance values, and has shown a very good leak test uh, results. When you do the post processings like vapor smoothing, you can further improve the water resistance in the material. So from here, we'll begin our other technology, which is again a laser powder bed fusion, named as DMLS. DMLS stands for Direct Metal Laser Solidification. It's kind of a micro laser welding process where thousands and hundreds and thousands of the layers weld together to form the 3D model in an inert atmosphere. So with the fact that they are inside a closed chamber, the properties and the defects probable are very minimum in the material. The chances of porosities and the chances of other foreign particle inclusions and defects are very minimum in this case. The MLS is available in aluminum alloys, steels, titanium, copper, nickel, cobalt, chrome, and many more other alloys, which are already tested and proven for EOS metal systems. And the technology is open to develop the new material as well. So you can use the same system to develop and convert the conventional form into the powder form, and then develop it for your printer. The operational stages for this is very simple in the fact that you have to understand the technology, but it involves the stages like material preparation and filling, same as the SLS. You have to do sievings and all, sieving of the powder, and then refilling in the machine, and then you have to start the printing. And after printing happens, the part goes under the oven to relieve the stresses, and then the parts are detached with the help of bend saw or wire cut, and then they goes for the post machining based on the requirement, what kind of tolerances you want, what kind of finishes you want. And finally, after the inspection, your part is ready for the final uses. The benefits of DMLS technology is, again, it's a tool-free technology. In order to get the castings or the forged or any component, you don't need literally any toolings. You don't need to develop the tooling. So it's very much flexible to iterate over the designs, and you have a flexibility to reuse the material. Once you use it, you can reuse it for further uh, number of cycles. It offers best-in-class mechanical properties. Even we have seen the DMLS 3D printed materials are 99.99x% dense relatively compared to the conventional forms, be it a casting or any other forms. It offers a high amount of repeatability over the processes. You can repeat the same quality over the cycles. The EOS systems are offered with the smart fusion technology, which is a kind of a intelligent proper technology with the laser that it automatically calibrates the power and reduces the amount of the material support material required, and it increases the productivity. So later on we'll discuss about the smart fusion technology also. it is it has the EOS system has integrated NDT kind of features also, which is a infrared feature where you get optical tomography inside the chamber itself. Once your part is ready, you can parallelly generate the entity report of your part, and you can investigate what kind of defects may or may not be in the part. So that's one of the feature, the unique feature is equipped in the EOS systems. So DMLS process is available, as I mentioned, in the form of the material. Like the type of the materials available are aluminum alloys. There are several kinds of aluminum alloys you can use for your PDC castings, or you can use for your sand castings or investment castings or extrusion forms. Any kind of component used in the industry, you can print them directly without tooling and using DMLS process. You can use the case hardened steel. uh, the chrome cobalt chrome material is available. Various kinds of stainless steels are available, SS17-4PH or 316L, or there are many more stainless steels materials available. There are tool materials also available which you can use for your pressure die casting or injection molding, tool manufacturing, or even if it is a uh, even if you want to make a soft tool or any other tools, you can use these tooling alloys. And this is available in titanium alloys. Nowadays it is available in copper alloys also. You can print a copper alloy, or you can print a commercially pure copper material directly through the laser based system. um, this is available in a broad category of nickel alloy also. You have a nickel alloy where you can seek it for the applications like high temperature or high oxidation resistance or high environmental crucial environmental applications. You can use this material over there. And there are few refractive materials also available with this system, and there are many more other alloys which are developed and introduced with the EOS system. And uh, you can also, as I earlier mentioned, you can develop your own material also through this system. So coming to the TRL, which stands for Technology Readiness Level Process Development, EOS classifies the technological maturity of all self-developed 3D printing SLS polymer materials and even 3D printing metal materials, and process using technology readiness level. So what are these TRLs? The TRL concept was developed by NASA and has since established itself in various industries. For example, level 5 corresponds, so you see the different levels before your screen. Level 5 corresponds to verification of the technical solution, and whereas level 9 corresponds to full production capability with the extensive statistical data. By providing valid parameters for parts properties, EOS makes your transition to additive series production faster and easier. EOS also divides its material and processes into two categories: core products span, which is typically from TRL 3 to 6, and premium products span TRL 7 to 9, which are ready for use in series production. One of the goal of the system is to offer new materials on the market with a clear value proposition. So this is how we place our processes with respect to the standards that are available. So I was explaining about the smart fusion. So smart fusion is again an add-on with the system, EOS system, and a unique value proposition that it's a thermal management system where we give the command to laser to calibrate and change over within the process from layer to layer wherever uh, the laser, the IR sensor sense the heat concentration, the laser decreases the power or increases the power, or changes in vice versa manner, to reduce the stresses, and to, thus you have a chance to reduce the support structures. You can increase the productivity. So the benefits upfront of adapting this technique is it can reduce it. It's been seen that up to 75% support structures can be reduced in structure roughly, and you can increase the productivity 2 times to even 5 times. It's been seen it is improved, and you can lower the cost per part. So far, we have discussed about prototype. You must be thinking, well, these all AM systems are available either for prototype, or there is a scope for production also. So in order to understand the production, we first need to understand what's the trend of AM within the industries, across industries. So earlier, in early days, we used to think the additive manufacturing is only used for prototyping purpose. Then a few times back, we started doing the small production of batches, and start improving the part quality, process robustness, and even optimization of cost per part. So today we are in stage where production can be ramped up with the best quality control and quality repeatability, and differentiations in many factors involved in the processes. The total cost of manufacturing can be reduced, and the system can be more automated with the technology integration. We are also seeing the future. Even we have been seeing the trend in a few developed countries like Singapore and Germany. People are facilitating multiple additive manufacturing machines to, and they're calling it a print farm concepts, which we call a digital factory. So you can literally have a AM cell within your plant, and you can have a SCADA based system where you just give a command for the AI based and optimized systems, and they will do the job for you, and literally it will guarantee the production. So that's how the evolution of additive manufacturing is working nowadays. So when we think about the production, we first have to look at the what is the part per cost, or cost per part, CPP, or a unit cost in a normal language. So first factor which comes in mind is the design. You have to optimize the design for additive. You have to focus how you can optimize it further to reduce the cost, and then you have to look at the pre-processing and production processes and post-processing. So these are the main factors where if you apply the optimization and you can establish a good value chain, you can end up with a good cost per part and reduce cost per part, which ensures the chances of converting the part in production for a particular machine or a AM system. So like any other technology, break-even exists for even conventional. So we tried forming the graph between the unit cost and the complexity, which we call a complexity graph. And on the other hand, we tried forming a graph between the unit cost and the volume. So when we call design complexity, where are the AM parts placed? Basically, it's been seen that the AM is additive manufacturing is applicable wherever the design is complicated, wherever subsequently the processes are complicated. So if your design is pretty complicated, like close to your complex castings, be it a complex casting or injection molded complex parts, it has more chances of getting converted into the additive manufacturing. So that's what the point of the first graph here is. You get a strong cost advantage with the complex design and processes. And while on the other hand, if you compare it with the volumetric graph, the more volume means the less cost in the conventional. That's pretty obvious. But what if you are able to optimize the design and reduce the volume? If you are able to choose the part which is in the mid-size category or a small size category, and you're choosing it for your particular system, that's where you start picking up, and you can implement the production process, the EM production process for a particular component and a particular system. So you can, by reducing the mass, by optimizing the topology, by reducing the size of the overall component, And of course, the quantity matters based on your requirement. You can switch to AM production systems, for example, for your spare part manufacturing or customized part. So here, in order to better understand, we have placed one case study on a geo console of an automotive. It's a fabrication model which is manufactured through different kinds of sheet metal operations followed by welding. So the best part here is with additive, we have leveraged the benefit of consolidating the child parts and making it as in an integrated way. For a particular AM system, we have seen up to certain number of quantities, which is 80 number of quantities. The additive manufacturing has shown its best cost over the conventional manufacturing. So it's very much evident. It depends. The production depends how you are selecting your component, how you are optimizing your design, and what system you are using for the production. Yeah. Moving forward, let's try to understand what is not value add, what is not value addition, or we call it conventional approach. So far, whoever are using the additive manufacturing in the industry, they are following the conventional approach. If we divide everything in the form of value chain, we get into 4 stages: complex design, AM production, manufacturing process, and functionality of the component. So the perfect case scenarios is that parts have to be optimized for AM, while in real case scenarios, we always try to manufacture the part uh, designed for and meant for conventional manufacturing. So that's where we are not able to leverage the additive manufacturing. The second value chain parameter, production. So when it comes to the production, we think that part performance will be high and increase the cost per part and saving achieved. But and in real case scenario, we see a very good advantage on this with the part performance increase, and some cost savings is also possible through optimization in the processes. In the third value chain, where manufacturing is there, manufacturing and assembly, typically we think that we'll be integrating the assembly. We have a chance to do the optimization, and we can reduce the number of assemblies concept. But in real case scenario, we make the component individually and we try to assemble them in a conventional manner. That's why we are not able to leverage the additive manufacturing technology for the production. And when it comes to functionality, in best case scenario, better product performance and less investment and lifetime cost. While if we look at the real case scenario, we get a better performance, but we are not able to save much on it due to many factors. So how to mitigate these situations and how to add the value through the additive manufacturing. So we saw the bottom to top approach. In order to leverage the technology we additive manufacturing, we have to do it in the other way around, the top to bottom approach. We have to reversify. We have to look at the functionality. We have to define the key value drivers, what are responsible for functionality, and then we have to optimize the processes. You can and evaluate the cost savings over there, and then we can establish the production process based on the production needs, and looking at all 3 factors, we can redesign the component and apply the design for additive manufacturing, which will be suitable for additive manufacturing, and you can easily adapt the production method. So with these processes, possibly you will be able to adopt all these processes only when you have a printer in-house. So I would like to show you what are all our printers available. In polymer, we have the different kinds of printers starting from small series, flexible, and large series and production. And in metal, we have small frame to production frame series. These varies with the sizes, with the number of lasers. So you please feel free to contact us in case if you are interested to look at the features and the commercials of the printer. So what are different applications available in SLS? You can look at developing the interior parts. There are many more applications which you can develop through SLS technology, all interior and functional parts. You can print dashboards, on-demand parts, or you can print AC vents, you can print central consoles and optical parts, and even optical housings. Exactly. There are applications like you can use FR material to develop the battery casings and battery products, and you can develop the charging stations component and charging plugs and fuel tanks, exterior component, molds and seating component. There are so many applications that you can implement SLS technology into. And then you can also use this technology to manufacture the fixtures or manufacturing aids, be it a testing fixture or a machining fixture, uh, in either of the technology, SLS and DMLS. Now moving to the DMLS, metal 3D printing. With metal 3D printing, you can print your PDC parts, you can print your different castings part, you can print the forging part, you can print sheet metal fabrication parts, you can print laser sintering parts, gear sintering, and you can print the customized toolings also to perform the machining. Typically, for last 2 decades, it's been seen that industry has been developing different kinds of component from the engine segment, be it from a transmission segment, and in a typical two-wheeler, we can see the body and chassis components. We can see exhaust components. So there are many more applications that industries are already doing it for prototyping and batch production also. In a typical four-wheeler, there are so many subsystems starting from engine, or in case of EV drive motor, we have a copper material for application of drive motors. And you can look at any component which is out of these two categories, polymer and metal. You can develop those using the additive manufacturing SLS and DMLS processes. And with this, I will hand over this webinar to take forward to our expert and guest, Mr. Joe from EOS. Joe, over to you, please.
Thank you, Arun. Hi, everyone. Too broad, Arun has given you very wide applications of additive manufacturing. I wanted to drill down to two value additions that SLS and DMLS technology will bring to automotive industry. So just like any industry, we use tools. That is number one. Secondly, we make direct products as well. With regard to tools, um, we have multiple varied tools, right from manufacturing jigs and fixtures, assembly fixtures, so on and so forth. One very unique application would be die-cast tools. This is one such part that is done by one of our customers overseas. This is a LPDC part made with aluminum. The end product is aluminum, and they see there are some areas where they have these smudges being formed. Some thermal mismanagement is happening, so you have very high hotspot. Things like that go wrong, right? So they told us, okay, what do we do about it? Because our end product quality is going down, right? So we said, okay, the traditional way of doing a cooling channel to properly maintain the temperature within the tool could be like this, the one that you see named as traditional design, where you have straight channels, so you are not able to remove the heat from tool properly. But if you could have a profile that is very close to the part profile or the product's profile, then you have a better control on temperature, tool temperature, whereby you could avoid all this product's quality related issues, whether it is in soldering, or if at all you wanted to increase the productivity, then probably during your cooling time, you can reduce your cooling time because you remove the heat directly from the product as such, right? In a very fast manner. So this is what they have done. They change the design which goes inside for cooling, and whereby now the hotspot which was 200 plus degrees is just 100 plus degrees, right? So if your hotspot reduces, then probably you have better cooling time, so which means your cycle time reduces it, which means your productivity increases directly, right? So this is one unique advantage I see, where we have little engineering that could help you along with additive manufacturing. Now, we are not into very mass production. So if at all people ask me saying, okay, when will additive manufacturing go into mass production? I say we start with tools. And this is one such application. In tools, we have varied classes of tools. The one that you see as stainless steel CX is predominantly done for high corrosive plastics such as PVC and things like that. And 1.2709, the other word for this is maraging steel. The name of this steel is called maraging steel, which is also an armor grade steel. So some of our customers use for armor application, right? It is a very through and through hardened material. We have H11 material, hot steel. We have H13 also coming up, and it is possible to nitride. You can even case harden it, these materials, and we see the one of the requirements of these die-cast inserts or even injection molding inserts is that very high surface finish. So as built you and shot pinked, you might have a surface finish less than 12 RA, which is about 10 condition, and we have a tolerance limits of a medium grade tolerance limits. Right after that, we machine it. So people also ask us saying, okay, I have a part, can I print it and then I get the finished part directly? No, it is not always the same. We have some post processing to finish it also, right, depending on different applications. This is one such application did for Silverado, the four-wheeler truck in US, and they wanted to reduce the build time. So there's one application where they introduce the conformal cooling channel and are able to realize this application. Coming to direct parts, predominantly automotive industry was the one who drove the rapid prototyping market, right? So under rapid prototyping, we had the vacuum casting technology, many other wax modeling, wood modeling, so on and so forth. And then came up 3D printing. Now, we are moving from this proto to pilot production stage, and in some cases, direct production, such as in EV also. If you ask us, overseas, we have three categories of applications that OEMs are driving. Number one is customization, where if somebody wants to have a unique feature for their cars, very personalized feature, then they go ahead with customization. And somebody wants to reduce their inventory to minimize their supply chain, probably then go ahead with digital spare parts, aftermarket parts. And sometimes you can also do a low volume production for some of these parts, where the tooling cost could be more higher than 3D printing, right? So this is one such application done by Mini, and this is basically side scuttles and trims where you can write your name and then you can print in your name, and it is very unique and it is for your application. Of course, the value here is customized product, right? Also, PSA did the internal door handle, which we pull to open the door, right? So this is that door handle, and that is 3D printed in metal, in fact, DMLS technology, by one of their service providers. What interests me is the keychains. If you personally ask me, I would make my own keychain, and very interesting application, right? Having our own keychains. In earlier days, we used to have simple keychains, like let's say your name starts with A or J, then we have a J keychain and things like that. Now imagine if we have some unique designs, then probably we can 3D print those designs and have it as a keychain also. And I take this example from medical industry, where this industry, let's say a patient has a fracture and he goes to doctor orthopedist and he says, I have a standard set of implants which I get it from a manufacturer, and then I give it to the patient, right? Now, what if the orthopedist go to a 3D printing manufacturer? He just has the raw material and it is very unique to that customer, right? It suits their requirement. This is what the customization industry is also thinking about. Can I make a customized product for one customer, right? This is the valuation that they think about. And of course, there is a little premium to it the cost also plays the factor. I read recently our business review, and they said Toyota makes small engine factory wherever they go, right? Whereas there was one case, GE Appliances, they had a very big factory and there was a fire accident and the losses were phenomenally high. So the idea is, can we have a very modular industry, very localized to that particular geography or demography, right? So and then meet those customers' need. That's the thought process, right? So what CAT have done is, this is one of their excavator product, and they printed a product in 80 hours time, which is roughly about 4 days, metal 3D printed part, right? And delivered it in 4 days time. Really amazing, right? Instead of shipping from one country to another country, locally printed and then give to the customer in 4 days time, less than a week. I think that makes a lot of economical sense. Similar to that is Daimler, who have also done a number of these parts were there, right? Almost 3 lakh parts were there for Evo buses. Some of these buses are very obsolete, and we cannot carry the inventory for a very long time, right? Especially if we work with defense, then probably we come in saying that, okay, for 10 years we at least support your asset, right? But beyond 10 years or beyond certain period, how are we going to sustain these assets? It's a big question mark. So they came to us and we worked along with them to screen these parts for additive manufacturing. And we said, okay, among 3 lakh parts, 2,600 parts will be suitable for additive manufacturing, for which you don't have to carry the inventory. And some of these parts were redesigned for additive manufacturing where they could enhance their functionality, right? The one that you see here is basically a conventional and 3D printed part, how they are using it basically. So that is how the localized factory is working up, planned to go. And another question people ask us is, okay, additive manufacturing, fantastic geometry, good value additions, and everybody is, looking looking at additive manufacturing. What will it offer? The biggest question is, how about the cost? Is it affordable, right? So let's say we work in lathe, right? Lathe or CNC, we work with parameters such as speed, feed, depth of cut, so on and so forth. Hardness of workpiece, hardness of tool, so on and so forth. We control these parameters in such a way that we meet the customer's requirement, is it not? Right? Similar way, additive manufacturing has a number of these parameters. They work around with these parameters and try to meet the cost without sacrificing the quality. Right? There's no trade for this quality, but how can we reduce the cost by optimizing these process parameters based on the need? One such example is here. Maybe what US is as a standard parameter that we gives you an RA value of 25 microns and a build time of roughly about 22 hours for 33 parts. Now, if you work a little bit, work on the parameters, you'll be able to achieve better surface finish, in as-built condition itself, and roughly about 40 minutes increase for the same 33 parts, right? This is where the intelligence of man comes from. Machine can do certain limit, but the direction that the machine can do is given by man, right? So we have to use our engineering minds and then see how can we optimize the cost. So here is one example where they have replaced the injection molded materials because of very low quantity, less than 50,000 pieces per annum, right? In plastics, they have done it, and today they have printed about more than a lakh of parts. Right? Directly replacement of injection molding. This is where Arun also showed you a template, or sorry, a table where he compared the injection molded polyamide 12 and then 3D printed polyamide 12. So it overlaps with within those tolerance bounds. Similar to that is a metal application where we have these LED heat sinks go behind our lamps, right? And if this has to be printed earlier, with the standard parameter, it was $40, right? None of us would buy a $40 heatsink, which we don't see it in our car, on the surface. It is not a garnish part, right? But after optimizing, it was affordable to $4, right? From $40 to $4. That's a phenomenal reduction. And this, if you ask me, I can afford it, right? So this is where we need to realize how the value that we have to play around, how can we optimize the cost, thereby we reach the exact critical to quality elements of our customer. So I stop here.
So I feel this is a better time to wind up our webinar, where I hope the audience have a good understanding about the additive manufacturing and its applications in automotive industry. So in case of any queries or any questions or doubts, or in case of any requirements, you can reach out to us. You can reach our industry experts, Mr. Lakshmi Narayan, as well as Mr. Arun Kashyap, and you can send your queries to the mentioned mail IDs as well. Thanks to all the panelists and all the audience for joining this session. Have a great evening and a weekend ahead. Thank you very much.